The first benefit of patterns we're going to talk about is their ability to facilitate systematic reuse of successful designs by codifying common roles and relationships among software components. When I developed the expression tree processing app, I didn't have to start from scratch. I didn't have to start from first principles. Instead, I was able to leverage the Gang of Four patterns that I had known, and were able to find ways to integrate those patterns into my software to help reduce risk and make it easier to build and sustain the end result. When I took a look at the various problems I faced as a designer, I realized I'd have to deal with the fact that there'd be different kinds of nodes in the expression tree: binary nodes, unary nodes, leaf nodes, and so on. And so I was able to connect the composite pattern from the Gang of Four book in order to help arrange the way the software worked for that part of the design space. I also knew I'd want to find ways to be able to replace different implementations over time, as I had different trade-offs I wanted to emphasize between time and space. In that case, I applied the Gang of Four bridge pattern to help make it easier to transparently replace implementations. I also knew that I'd have to find some way to be able to read the input that was provided, either from a user interface or the command line, convert it into a parse tree, and then create an expression tree from that parse tree. So I was able to apply the interpreter and builder patterns. Likewise, I knew I'd have to find a way to be able to traverse an expression tree and traverse it in multiple traversal orders and be able to apply various operations to the tree to print it, to evaluate it, to do various other kinds of analysis and optimization, and so forth. For those various tasks, I was able to apply the iterator, strategy, and visitor patterns. And all those patterns, and many more that we've discussed, help to greatly reduce the amount of effort required to build and maintain this software. So patterns are great at being able to systematically address the roles and responsibilities that have been known to succeed from previous work. One of the other benefits of patterns is their ability to be able to record the engineering trade-offs and design alternatives that we need to be able to enhance development and sustainment over the life cycle of software. If you recall our discussion of the template method pattern in Lesson 5, we discussed the fact that there was an alternative way of being able to provide the solution, one based on the strategy. And the main issue there was whether or not we were going to have dynamic changes to the different modes that operated our application, or whether we were simply trying to make sure that we could address those different modes at design time and compile time. For our particular set of trade-offs and our particular needs, it turned out that template method worked fine because it was fairly simple and we didn't really need all the dynamism that comes from using strategy. In other cases, however, strategy is the right way to go. And so by being able to understand these trade-offs and document them in the form of patterns greatly helps people to be able to work together and understand these design decisions when they have to maintain code, especially if the code was something they didn't write in the first place. This leads to the next benefit of patterns, the ability to be able to define a shared design vocabulary that enhances understanding, team communication, and helps to reduce the effort of engineering and re-engineering software. For example, if you take a look at the use of the interpreter pattern and the builder pattern in the expression tree processing app, it turns out that there's lots and lots of classes involved. There's classes involved in parsing the input, creating the parse tree, then taking the parse tree and using that to create the expression tree and so on. And if you were just to look at the reductionist pieces, the classes, the interfaces, the objects, the methods, you might be overwhelmed by the number of various entities involved. However, if you apply patterns, you can greatly reduce the surface area of the design space. So instead of having to think in terms of many, many disconnected classes and methods and objects, instead you can think about a few patterns like builder and composite. And the knowledge of this, by chunking together these pieces, is tremendously useful to allow people to communicate more effectively, to help guide what it is they do as developers. Another benefit of patterns is it helps to provide the basis for automation. Sometimes the automation is relatively simple. For example, we talked before about how patterns over time basically codify best practices and design conventions and programming conventions. And oftentimes the most useful of these and the most long-lived end up being realized in the form of programming language features. For example, you can think about the way that C++ and Java and other object-oriented languages have essentially automated the iterator pattern in the form of various kinds of loops, the range-based for loop in C++, the Java for each loop, and so on. So that's an example of providing basis for automation in a relatively simple way. Of course, there are much more sophisticated and powerful forms of automation that are also patterns-oriented as well. For example, there's a whole design paradigm called model-driven engineering, which uses so-called domain-specific languages and domain-specific modeling languages to be able to express designs at a higher level, more at the domain level, by using tools that represent various abstractions in a way that's representative to subject matter experts and domain experts within a particular context. And these high-level designs, which are often graphical in nature, using symbology and notations that are representative of the domain, can then be automatically generated into code, which is correct by construction, thereby allowing you to work at a higher level of abstraction without getting caught up in the details of all the different programming elements at the traditional third generation level. So this is another example of how we can automate certain patterns. It's of course important to realize that you can't automate all patterns, but we're starting to move little by little in the direction of trying to automate the things where it does make sense. Patterns also make it possible to help transcend language-centric biases. So not surprisingly, many people feel very, very passionately about the programming languages that they use to build software. And this is great. I'm a big fan of using good languages. I've used many languages throughout my career. But one of the things I've noticed is if people get too carried away with programming languages, they tend to be distracted from what really matters, especially in large-scale systems, systems that are going to live for a long time, have many people involved with them, mission-critical or safety-critical behavior. In those kinds of environments, the programming languages are important, but they're relatively tactical in scope. And what's really strategic is understanding the key architectural issues, the component relationships, and the patterns that help guide and weave all those various elements together. Patterns also help to abstract away from non-essential detail when it doesn't matter. For example, in the design phase, the goal is really to identify the key roles and responsibilities of the main entities in a particular solution space, and not to get wrapped around the axle of a particular implementation technique, the use of linked lists versus vectors or so on. It's really to focus on a more holistic perspective, to plan out how the various parts fit together. And patterns help us to focus on those more strategic dimensions, deferring the implementation decisions to where they belong in later phases of the overall design.